In example 6, the fastest drag racers can reach a speed of 330 miles per hour over a quarter-mile strip in 4.45 seconds from a standing start. By virtue of the mean value theorem, we know that at some point during the race, the acceleration of the racer must have reached what? Okay, so the mean value theorem is talking about continuous and differentiable functions. So the first thing I need to argue is that my velocity is continuous and differentiable. So velocity is, so first of all, continuous. Why is velocity continuous? And then why is it differentiable? Okay, velocity has to be continuous because your speed is going to be connected. You can't jump from one speed to the other without jumping through. It's just the way physics works. They're both going to be because of physics. And differentiable because it's got to smoothly connect. You can't connect through one speed to the next speed without getting to the speeds that go between them. So it's got to be smooth to get to the next velocity. You're going to have to get to every velocity that goes up there. Okay, you can't, even if you abruptly change your velocity, you are going to get to every velocity between. You don't get to jump your velocities without changing. So just because of the way physics works, velocity is always a smooth, so continuous and differentiable function. So hopefully we can agree with that. If those two conditions are checked, then we can use the mean value theorem. And the mean value theorem says that if I know an average velocity, I'm going to be, if I know an average acceleration, I'm going to be able to guarantee the existence of an instantaneous acceleration. So if I had two ordered pairs, like I know that the speed of 330 miles per hour can be reached in 4.5 seconds from a standing start meaning initially 0, 0, then I can figure out what the average acceleration must have been. Okay, so if we do our 330 miles per hour divided by 4.45 seconds, I don't know how that divides out, let's find out. That gives me 300, I put an extra 0 there. 330 divided by 4.45. That gives us 74.157. Okay. And the units on this are miles per hour per second right now. Okay. This is our secant slope, so by the mean value theorem, we can conclude there exists a c in the interval 0 to 4.45 such that v prime of c, the derivative of velocity, is acceleration, so a of c equals that 74.157. miles per hour per second. Okay. So the mean value theorem proves the existence of that c. So the acceleration of the racer must have reached 74.145 miles per hour per second during the race. Alright, and our last page deals with consequences of the mean value theorem. See if we can spot how the mean value theorem leads to each of these important conclusions. The derivative implies, zero derivative implies constant function. If f is differentiable and the derivative is equal to 0 at all points in the open interval, then f is a constant function. So algebraically, if the derivative is equal to 0, that means that the two y values is equal to 0. So the slope is equal to 0 for any given function, for any given point, so it means that the function had to be constant. So if the slope equals 0, that implies that the two y values had to be equal, so it implies your function had to be constant. So the mean value theorem leads to this theorem. The next one, functions with equal derivatives differ by a constant. So if two functions have a property that the derivatives are equal on an open interval, then the difference of the two has to be constant. Okay? So if the derivative was equal to 2 for all x, so this is the slope being equal to 2. What's the scale on this thing? So if the slope was equal to 2, then I could draw something that had a slope of 2 anywhere, and they're just going to differ by a constant. So like these are two linears, for example, that have a slope of 2. They just differ by a constant. So the mean value theorem helps us to see that as well.